This is the outline of our work. First, I introduce the background of value-aware celebrative data pricing for federated learning in vehicular networks, and discuss the motivation of our work. Then I detail the system model and our proposal, followed by the performance evolution. Finally, I give the conclusions and future work. With the rapid development of 6G and vehicular networks (VNets), a large number of machine learning tasks has been generated to provide people with smart services such as vehicle positioning and road conditions classification. Federated learning allows each data owner to locally train the collected data and to upload local update to central server, reducing communication overhead and improving data security. Therefore, federated learning as a new learning architecture has attracted widespread attention to support various applications and services in VNets. The continuous expansion of federated learning in VNets promotes data transition. Federated learning technology builds models based on data. On the one hand, central server incentives VNS to participate in VFL for improving the accuracy of model. On the other hand, VNS cooperate with each other to maximize their own utility. Next, I introduce the motivation of our work. When performing learning tasks, they hear the quality of data, they hear the quality of local model update. Consequently, we use data quality as the basis for pricing. VNS usually generate and collect data in different ways. As a result, the number and characteristics of data owned by different VNS may vary greatly. Therefore, the data of VFL is non-independent and identically distributed. In addition, outdated data may reduce the accuracy of the training model, leading to wrong judgments and low quality of experience of the test requester. As shellfish and regional nodes, VNS will not actively participate in the training process of the VFL task, and the existing works typically think that VNS independently price data, which lacks the consideration of the cooperation among VNS to increase their data value and maximize their utility. Therefore, we proposed a value-aware data pricing scheme to facilitate the VFL in VNet by considering the quality of data and the cooperation among VNS. Next, I introduced the system model, including the network model in the VNet and the task model in the federated learning process. I first introduced the next model, as shown as in this figure. The networks consist of task requester, central server, and VNS in the VNet. Central server, as the controller of the VFL, is responsible for assigning VFL task from the task requester, catches data and press information of VNS, and aggregates global model. If a task requester has a learning task needs to be completed, it can publish the task to the central server. After the central server completed the learning task, the trained model then can be delivered to the task requester VNS in the VNS, including UAV, CBS, and RSU, can decide the process of its data and execute the local training based on the pricing model broadcasted by the central server. If the VN is selected by the central server to train the learning model, the reward will be paid to the VN after the learning task is completed. The size of learning task in the VNS is denoted as the size of capital R. For task R, it can be represented as the first formula, including the unique identification, the description of task R, and the reward for completing task R, which is provided by task requester. Then, the central server broadcasts a request message to the VNS in its communication carriage, shown as the second formula, including the machine learning model, which is selected by the central server for task R. The initial parameter of the machine learning model, the number of epochs The local batch sets used for local training the requested number of samples in each round for training the learning task. Next, I introduce our pro-service the data transition architecture for VFL and the collection game analysis based on data value. I first introduced the data transition architecture for VFL. The data transition architecture designed for the VFL has the following steps. A. When a task requester has a task to be completed, it first describes the detailed information of the task as a task requirement message and sends it to the central server. B. After receiving task R from the task requester, the central server initializes the module parameters and sends the task release message to VNS. C. Based on the information of the task request and the VNS, the central server starts to operate the collection game. Specifically, for each VNS, it decides its date price based on the value of its date, where the price model is determined by the central server. Furthermore, it can form a collection by itself to train the model individually, or form a collection with other VNS to increase its date value. D. Based on the date prices and the value of different collections, the central server selects a group of collections to form optimal collection set using the date from the OCS to train model. E. When VN starts to execute the capital K runs learning task if the VN is a member of the OCS. F. For each VN in the OCS, it sends the local update to the central server if the local training is completed. G. The central server aggregates the local updates received from the VNS into a new global model. In the VFL, VNS with different date values have different contributions to the global model training. In general, the data owned by different VNS are heterogeneous. Therefore, we define date value by jointly considering two factors, non-IID and AOD. Average Earth movies distance (EMD) can be used to measure the heterogeneity of data distribution among different VNS. The non-IID of collection is represented as the first formula, and to make EMD and AOD in the same order of magnitude, we use min-max normalization. AOD can be used to evaluate the freshness of data for collection SG. The AOD can be defined by the formula on the left, and INC-I is the AOD of dataset owned by VNI. We measure the value of data by its heterogeneity and age. In this way, based on the non-IID and AOD of data owned by different VNS, the value of the data owned by collection SG can be expressed as the formula on the right, which rho is the parameter to balance the importance of the non-IID and the AOD. A collection game can be expressed as IVSG, where I is a set of VNS which take part in the collection game. SG is an arbitrary subset of I, and VSG is a characteristic function of collection SG. In the collection game, the characteristic function VSG represented the utility of the collection. The data value and the data volume of the collection will affect the global model of VFL. Therefore, we can define the utility of the collection by the formula. For collection conditions, the utility after the node merged in the new collection is larger than the utility of the node in previous collection. In the collection In addition, the utility obtained by each VN after VNR is merged in the collection is no less than the utility obtained by the VN in this collection. If the conditions are satisfied, the collection structure is shown as this. If VNR in collection SG participates in the round of federated learning training and contributes the global model, it will obtain the corresponding reward. Because the data value of different nodes is not the same, the contribution of the whole collection is different. Therefore, we can calculate the utility of each VN in the collection based on its contribution. We have this. In the process of the data transition, each node tries to merge to form a collection according to the collection conditions and the collection principles, and finally forms a stable collection structure through multiple rounds of collection formal process. The process of collection can be described as follows. First, the nodes are divided into capital collections where each collection has only one VN. This is the initial collection structure for VNI. There is a collection sequence SQI that includes the remaining collections is packed SG. Shown as this, VNI selects a collection from SQI in turn. If the collection conditions are satisfied, VNI merges in the collection according to the collection principle. In this way, each VN is analyzed by collection game in turn until the stable collection structure is achieved. In the data transition process, the central server intends to obtain the highest quality data with the lowest rewards. Therefore, we define the collection tab by considering value of data and the price of data to help the central server make a decision. The collection tab represents the central server's performance for collections. The higher order of the tab of SG implies that the collection has larger possibility to contribute its data. Then the tab of collection SG can be defined as this. When the collection structure is stable, there are capital G star collections. Sort by the collections based on the tab. In ascending order, there are two cases to form the OCS. First, if DR is less than DSG, the central server selects DR data from the collection. We have DSG equal to DR. In this case, collection provides DR data to train global model. Second, if DR is more than DSG, we have DR equal to DR minus DSG, namely the collection provides all data to train the global model. Repeat this process until we have DR less than DSG, then the case is similar to case 1. After introducing our process, we then move to the performance evolution. First, I introduce the simulation conditions. The dataset used in our communication is C14 dataset. C14 is divided into 5 batches, training sets, and 1 batches test set. Each batch consists of 10,000 images, where the dataset contains 10 labels. The occurrence probability of each category of image is essentially equal. Therefore, we set the ideal distribution of the data is 0.1. Each VN randomly extracts 100 images as its own data set. The weight of EMD in this value is set to be 0.5. The weight of the collection utility is 0.1. The performance of process scheme is evaluated by comparing with the follow conventional schemes, non-cooperation schemes, NCS. In this scheme, all the VNS provide its data to train the learning model independently. Big collection scheme, BCS. In this scheme, all the VNS form a big collection and provide their data to collect the learning task celebratively. The first figure shows the average utility of the VNS increases with an increase of row because the proportion of data in MD will cause more data value. The second figure shows the average utility of the VNS increases with an increase of the number of VNS participating in the learning process because the increase of nodes promotes the variability of the collection structure, where the probability of collection with low heterogeneity become high. At last, I summarize our paper with collections and the future work. We have proposed a value-aware data pricing scheme to facilitate the VFL in VNet. In the scheme, we have designed a novel data transition architecture based on the value of data and the cooperation among VNS. Then, by considering the non-ID and AOD, we have developed a value model and evaluate the quality of data next with different values of data owned by different VNS. A distributed collection function game has been designed to promote the cooperation among VNS, where the equilibrium of a collection game has been obtained by designing a collection form algorithm. Similar results have demonstrated that the Proso scheme can achieve the optimal strategy for VNS and outperform the conventional schemes in terms of the average utility obtained by VNS. For the future work, the integration of blockchain and the proposed scheme will be considered to generate the security of the VFL in VNet. That's all. Thank you.